Now, it would be very tempting to just kind of start filling this worksheet from top to bottom. But what did we learn? We really need to systematically come up with loop invariants, and then we should pick a loop invariant, and then we should use it to help us derive the program to be correct. So how do we come up with a loop invariant? Well, it's going to be all about the post condition. So let's erase this. Let's put the post condition front and center. And let's remember that we march through these vectors in a very consistent way. At some point, x can be thought of as a top part and a bottom part, and y can be thought of as a top part and a bottom part. And the loop invariant really tells us what has been computed so far with these parts. So what do we have there? Well, what we're going to do is we're going to take this and plug it into the post condition, and that's going to be just like splitting the range when we use the other notation. So we get alpha is equal to x top, x bottom, dot product with y top, y bottom, added to alpha hat. And what we saw before was that this partitioned dot product equals the dot product of the top parts plus the dot product of the bottom parts plus the original contents of alpha hat, and that is now what our alpha equals. So what is this? This is really the equivalent statement that you would get if you expressed this operation with a quantifier and then split the range. Implicit in this, of course, is that x top must be of the same size as y top, because otherwise this dot product doesn't make any sense and that dot product doesn't make any sense. Okay? This we call the partitioned matrix expression. Or PME. And it's from the PME that we are now going to systematically derive loop invariants. So one quick comment about the partitioned matrix expression. Notice that we say matrix expression, and that's because this came out of our research on matrix computations. And notice that often we will just view a vector as a special case of a matrix. So here, we take matrix in a very broad sense. For those of you who have a little bit more experience with computer science, the partitioned matrix expression is actually a recursive definition of the operation. And what we're going to see as the course goes on is that if you have the recursive definition for the operation, then we know how to turn it into a loop-based algorithm. Okay, so let's move on. This, in terms of the partitioned vectors, is everything that needs to be computed. Okay? All we're saying is partition the range. What we need is a loop invariant. And what is a loop invariant? A loop invariant is a partial result towards the final result. So, what did we do before? We looked at the expression of what needed to be computed. We split the range, and then we said, well, one part of this has not yet been done. And we can do exactly the same thing here. We can say, look, as we're computing, we've only computed with the top parts of the vectors, and we have not yet done any computation with the bottom parts of the vectors. That's a loop invariant. Or we can say, we've computed with the bottom parts of the vectors, but not yet with the top parts of the vectors, and that's a loop invariant. That just means that we go through the vectors backwards. So the idea is the partitioned matrix expression, in terms of the pieces of the vectors that we naturally deal with, expresses everything that needs to be done. Coming up with loop invariants is then saying, oh, but we've only done a partial result towards that final result. So, what does that mean? That means that we now have two loop invariants. And we'll call them invariant 1. And that would be alpha is equal to the dot product of the top parts plus the original contents. And invariant 2. And that's just the dot product of the bottom parts plus the original contents. Ta-da! We have systematically derived two loop invariants. So now what do we need to do? Well, we need to pick one of these loop invariants and fill it in our worksheet everywhere where it needs to be true. And then we're ready to derive everything else, which we saw previously is then completely determined by that loop invariant. Okay, so what do we do now? We take the loop invariant and we fill it out, and we know that it has to be true in 4 different places before the loop. After the loop completes. Before the loop body. In other words, once you enter the loop, and every time at the top of the loop. And at the bottom of the loop. But what else do we know? We know that there's a loop guard G that keeps us in the loop. That still has to be true every time we are at the top of the loop, and that becomes false when we are done.